Hey guys, so to be totally honest with you, I never really liked the way that my 5/8 notes went before, so that's why I cut that last video short, because I wanted to talk to you a little more in depth about like real world application problems, not just like random points. So let's just review from the last video, right? If you have 3 points, that's going to make a perfect x squared graph, right? If you have 4 points, and they have to pass a vertical line test, that's going to make a perfect x cubed graph. If you have 2 points, that's going to make a perfect linear graph. So that's nice in terms of like data points and making an equation. However, like not everything's going to be perfect. And if you didn't realize yet, guys, the real world, not exactly what we call perfect, is it? All right, so let's talk about polynomials in the real world. We are going to go ahead and try to fit data to linear, quadratic, cubic, or quartic models. And we're going to take a look at our first application problem, and it's about food production. This chart over here, if you look, it's not really a chart, it's more of a picture. But if you look over here, this chart shows how much milk Wisconsin dairy farms produced in 1955, that they produced in 1980, and that they produced in 2005. We're going to use a graphing calculator, or if you don't have one because you're an at-home learner, you're going to need to find a website that can do this to model this data. If you can't find a website, please reach out. I'm going to make that your responsibility. I do believe the one provided in 5.1 would work. All right, so first of all, let's get some points and let's be very careful to indicate what we're going to let x equal. So let's zoom in here. Whenever you have really big independent numbers like this, we need to think in terms of time. So I'm going to let x equal the years since 1900. Okay? So my first data point is going to be 55 for 1955 and 16.5. This will be 80 for 1980 and 22.4. And this will be 105 for 2005. Remember how that's 105 years after 1900 and 22.9. So there's my points. Now this is in billions of pounds. So in 1955, that's when my parents were born, there was 16.5 billions of pounds of milk produced at this Wisconsin dairy farms. So let's talk about the linear model. So I'm going to get a calculator. I'm going to hope that this TI-84 will work well. And I'm going to clear this out. I want to look at a graph. In fact, you know what? I know that one does not do regression. So what I'm going to need to do is grab Desmos. So give me a second to do that. Grab my Desmos graphing. There it is. I'm going to put my points in here. So I'm going to create a table. And in fact, you know what? This calculator can do at least this much. So maybe I'll type it in this one so you can have a good visual for when you get to school, those of you who are coming in. Okay, so let's go to Stat and Edit. I'm going to clear out what I have here in L1 and L2. And I'm going to type in my X values of 55, 80, and 105. I'm going to go to my Y's. I'm going to type in 16.5, 22.4. Remember, these are billions of pounds of milk, and 22.9. Now that I have that in there, I want to talk to you about what a good window range would be. For my XY window, I'm going to start with going from, we can make that a little better. This is my XY window on my calculator. My x-axis, I'm going to go from 0, which remember 0 represents 1900, all the way to, I'm going to go to 2050, so 150. Please remember that the year 0 represents 1900, and 150 is going to represent 2050. For my y-axis, I'm going to also start at 0, which represents 0 billions of pounds, and I only need to really go up to 23, so I'm going to go all the way up. I'll just go all the way, I'll go to 50. Let's see what that looks like. So I'm going to go to my window. I'm going to go from 0 to 150. And my minimum on my y's, I'll go from 0 to 50. When I hit graph, hopefully I'll see my points. Clear out my y equals. I don't need to see that. And if your plots are not on, you might need to turn them on. I'm going to turn my plots on. Now I'll hit graph. There they are. Those look pretty good. All right, so those are my points right there, okay? Those are the different points. So what we're going to come up with first is what we call a linear model. I do ask you to insert the graph, so I'm going to do that now. There we go. That looks pretty good. I'm happy with that. And let me go full screen on Notability. That looks nice. All right. So if you want to put some labels on there, you're more than welcome to, right? This is from 1900. And this is 2050. And this is from 0. I do believe we went up to 50 for the milk production. And you can carry that graph over to the other side as well. Now to do a linear model, I'm going to show you what that would be on the calculator. Now you got to remember, I don't pay for the pro version here, but I will walk through the steps, okay? I have the answer key beside me. So I would go to Stat, just like I always have, and I would go over to Calc. For the linear model, I would select number 4. So let's just make sure we make note that we're going to go to Stat. We're going to go over to Calc. We're going to select number 4 because that's the linear model. Now what I'm going to do is I'm going to tell you what your calculator would give you, okay? If you were to work this out, I can't because I did not pay for the pro version. You would get y equals an a value of 0.128, which is your slope, and you would get a b value of 10.36. Now those can be rounded numbers, but that's what we would get if we were to go ahead and proceed through and get a linear model using our calculator. I do believe Desmos graphing calculator does this. Maybe at the end I'll figure out how to do that. Let's also acknowledge that your calculator would tell you that r squared is equal to 0.8, essentially 0.81. That tells you how accurate the fit is. Now what I want to do is come up with a different type of model, and that'll be a quadratic model or a parabola. So on this one, you would do the exact same thing, right? You would go to Stat, Edit, you would type all your stuff in, but this time you would pick quadratic is number 5, okay? On the calculator, you can see it right here on the side. And I will tell you, if you do the quadratic model, you will get, again, I have the answer key here. Give me a moment, I want to come up with the answer for you. I'm going to show you how to do this on Desmos. At least I'm going to try my best. So I'm going to put my table in here, 55, 80, and 105. And I did that by inserting a table. And my y value is 16.5, 22.4, and 22.9. Please forgive me as I struggle through this, but I want to change my window to be what I had in my other calculator. Bear with me, please. I'm hoping that you are also doing this with me. Otherwise, it's kind of silly for me to be working on it. There are my points. Now, I do believe I can do this here. In order to do a quadratic, I've done this before, I can do this. It's going to be y is approximately a x sub 1. That's telling me to put and then we're going to square those. That's how we do quadratics. And then plus b x sub 1. We're pulling our x's from the sub 1 category up top. And then plus c. I do believe I'm doing okay so far. Oh, I apologize. This y needed to say y sub 1, so I need to go back to it and make it y sub 1. There we go. Now I have everything I need. I have the values of A, B, and C. You can notice, please, how it goes through those 3 points perfectly, doesn't it? So I'm just going to take a quick, I'll do a quick dual screen here. Thank you, Desmos. Now again, if you were using a handheld calculator, it would actually be a little bit easier. So it's y equals, the A value is negative 0.00432, and that's x squared. This is standard form of a parabola, plus 0.8192, and that would have an x. And then the C value is minus 15.488. Your calculator that sits on your desk, that would give you A, B, and C as well, so you would end up here. And let's look at the fact that r squared is 1, okay? Now what I'm going to do is, I'm going to actually go back to my handheld calculator, like as if I was in school. So I had one of these calculators here, okay? And here's what we're going to do next. I'm very much hoping that you're doing this with me as much as possible on your own calculators. Otherwise, this is kind of a moot point. All right, so remember how we have those 3 points there. Now what we're going to do is we're going to go to y equals. We're going to type in our linear equation first. 0.128x plus 10.36. And then what we're going to do is graph that. I want you to see this line that was created. In fact, I'm actually going to get rid of this one, if I knew how. There it is. And instead, I'm going to replace it with this one. So what we're seeing here, we're seeing how well a linear model, meaning a linear equation, fits our information. Let me zoom this down, put it here, and erase these numbers, zoom it in so I can see a little bit better. That looks pretty good if you ask me. So remember, we were looking at 0, which is 1900, to 2050, 0, and then to 50 billions of pounds of milk being produced. What I want you to notice is that this is not perfect. These points do not exactly lie on our line, but we do have a linear model. Now what we're going to do is the exact same thing, but we're going to do it with our quadratic model that we discovered. Get rid of that. Go to my, clear that out. Let's type this one in instead. So it was negative 0.00432 x squared plus 0.8192 x minus 15.488. Now watch what happens when we hit graph. It is my hope that as you look at this graph, while I kind of fumble around here, that would have been 50 way up there, huh? Might need to redo that other one. It is my hope that when, sorry, I just got a big email, that when you see this graph, that you notice it fits them perfectly. Look at those really nice, look how they go exactly through those points. And over here, guys, I did make a mistake. This wasn't 50 anymore because I had zoomed in. But this is still 1900 to 2050. And that is still billions of pounds, and then whatever that is, what it was up there. All right, so now that we have our linear model and our quadratic model, let's talk about them a little bit. In fact, let's plug in some stuff. So the question asks us, the next question down says, all right, so you have your 3 points represented in each graph. There they are. And it says, estimate the milk that's been produced in the year 2000 with each model. Step 1, we don't plug in 2000. Remember, the year 2000 means that X is 100 years past 1900. Please do that over here as well. So I'm going to take my equation, y equals 0.128. I'm going to multiply it by 100 because that's what I need to be plugging in, 10.36. And I will substitute that in. In fact, I'm going to use my calculator to my advantage to do that. If you want to do it by hand, you are more than welcome to do so. I'll just type that in my y2, 0.128x plus 10.36 just to save me some time for future. Shift and table this time. All right, so this one you can plug it in by hand, right? You can take this equation and you can put it in for x. I meant to hit duplicate there. You would think that I'm embarrassed, but I'm not. Okay, so you see those x's. You're going to put 100 in for those x's. And my calculator just did it for me automatically. So my first one over here, my red one, I'm going to type in 100. So that plugs in 100 for me. And I end up getting 23.23. And that's right here. And then with this one, when I plugged in 100, you get 23.16. Now we need to make statements. If you use the linear model, you can say in the year 2000 that this Wisconsin dairy farms produced 23.16, and I do believe this was in billions of pounds of milk. And if you use the quadratic, you could say that it produced, instead of 23.16, it would say 23.23. And I'll put a period after billions because that looks kind of silly. Billions of pounds of milk. So the question becomes like, wow, those were both semi like the same, right? And the year 2000 is going to be right somewhere over there. You can see the year 2000 is going to be right before this point. Year 2000 somewhere right about there. So you can say, wow, it really didn't make a difference if you use the linear or quadratic model. Thanks for wasting my time. But you have to remember, sometimes models are better for interpolation, where you're like finding data points in between like we just did. And then sometimes there's other ones that are better when you do extrapolation, when you look outside of the data point. So what I want to do is I want to focus on 2030. 2030 is outside of our data, okay? That would be extrapolation, where we're looking outside of our data. So we're going to plug in 130. So I'm going to make x equal 130, and we're going to talk about which one makes more sense for this particular estimate. So I'm going to grab my calculator. Remember how we typed them into our y equals, and hopefully you did as well. Again, otherwise this is just completely useless. And we're not here to waste our time, are we? So let's type 130. And remember over here, this blue one, that's my linear model. So if I would do, if I were to plug in 130, or substitute in would be my big girl word, that would say that in the year 2030, that they were predicted, remember this is a future, it's a prediction, predicted to produce, well, how much? 27 billion pounds of milk. That doesn't sound so outrageous. Now let's plug 130 into our quadratic. I mean, just because I feel a little lazy. Put that over here so I can just type erase. What does our quadratic model give us? If you put in, look at that. If you use the quadratic model, it predicts it to only be 18 billions of pounds of milk. Now it's time, guys. It's time to like discuss this. Which one do you think is a better estimate here? Because I would honestly say here in the year 2000, they're pretty much the same, right? Like either one's pretty good. But down here, which one would you say is a better predictor? Would you say the linear model or the quadratic model? And maybe you're thinking, well, hey, the quadratic model is perfect, right? R squared was 1. That means it's a perfect fit. But I would like to defend the linear model in this because I can't really see unless maybe something happens where, Wisconsin doesn't produce as much milk, but like if the pattern continued, I would say that it would continue more on a linear model than it would on the quadratic model because the quadratic model starts going back downhill and it doesn't really look like that's going to be the idea for this particular farm. So while the quadratic model might be a perfect fit overall with an equation, logistically speaking, for future predictions, I would have to give the edge to the linear model, even though it's at an 81 and the quadratic's at 100. So you need to be able to say, like, I'm going to reason through this, and I'm going to say that the linear model, maybe for future values, is going to be better. So I'm going to use this fancy word for you, okay? You ready? So the linear model is a little bit better for what we call when we want to extrapolate, means we want to look at stuff outside. So there's a fancy word. Are you ready? I'm looking it up to make sure I don't sound like an idiot when I spell it here. Extrapolation. Extrap, meaning it might be better for data outside our range. Or maybe the quadratic model. The quadratic model might just be better for what we call interpolation, which means data inside our data set, because inside of there, it's pretty much, it fits pretty well. There we go. So better for. So as mathematicians, it's really important to be able to look at a graph and say, hey, this is probably better to use here, or maybe it's better to use here. Which one's better for a particular time frame? Now that's it for this particular example. I redid that one, so I'm going to stop here and perhaps I'll come back and talk about the cubic version of this as well.